All right, hello everyone, and welcome to the third installment of our Transformers series. Today we're going to be going over encoders and decoders, or an encoder-decoder model. If you'll remember, encoders are generally good at classifying things or performing some sort of mutation on data to get an inference, and our decoders are generally good at generating new data. Or new data based on the data that it trained on. So encoder-decoder models tend to do a combination of the two, and we're going to be learning about something called conditional generation today, which is fantastic for a lot of different things. We're going to use it for classifying, but you could ostensibly do something like translation or summarization or code generation. There's a lot of different applications that are really cool with these models. So yeah, we are gonna do classification of emotions. This shouldn't be a problem at all, and this should feel really familiar. So from Transformers, import T5 tokenizer. This model is T5. So T5 is text-to-text transfer transformer, and basically what happened was the transformer architecture was created with attention is all you need, and then BERT was created not too long after, which was an encoder only model, and then GPT was created not long after, which is a decoder only model, and then after a couple of years Google came back and created T5, which is an encoder-decoder model emulating the original Transformer model, just to show everyone that it was still the best. And it blew a whole bunch of stuff out of the water on the glue and super glue tasks, which was really cool. And we are going to do data collator with padding this time. And then we need training arguments, and we need our trainer. Perfect. And then from datasets, import load dataset. And then from sklearn.metrics, import, and we're going to grab the F1 score and the accuracy score. This is so that I can help you guys learn about how to do compute metrics to grab your own metrics as this trains. ds equals load dataset, and this is what it looks like when you're loading a dataset just completely from the Transformers hub instead of anywhere else. So we're going to load their emotion dataset, and then we're going to print what does that look like, and then we're going to print the first row. We have to index into train. I suppose we could do one of each of these for, because you're going to see, like in the last video, I talked about how these data sets on the hub generally have a training, a validation, and then a test. Yeah, here we have our training data set, our validation data set, and our test data set, and you'll see that they're different. And this is another important thing. All of the labels are they're already encoded numerically, so we don't have to worry about that as much as we're going through here. Normally you're going to have to change your labels into a tokenized version as well, and we'll run them through a tokenizer, but it's not going to do a whole lot for these labels, as you'll see. Let's do that right now, actually. So just like normal, we are going to create a tokenization line. Oh, actually, hey, let's do this first. I completely forgot to even import our model. So model checkpoint, just so that this is so that we don't have to write this multiple times, but we're grabbing the T5 V1.1 It's an underscore, but we're grabbing the base model. The tokenizer is going to be T5 tokenizer from pre-trained model checkpoint. We're going to scroll down so that I can actually see the suggestions that it posts. Model is T5 for conditional generation from pre-trained model checkpoint. And you'll notice if you're getting used to this, we're not initializing with a config. I wanted to show you guys that, I mean, you can probably extrapolate. I don't want to pretend like you guys are not smart, but this is what it looks like when you initialize without a config file. I still recommend doing it every time. I'm just getting a little bit lazy with these. It helps every single time to just know what the default parameters are. This is a language model, so generally you're going to have 768 dimensions on your embeddings, and the vocabulary size, all of that stuff. It's good to know it. It's good to be really familiar with your model, because the model is a little bit less important than understanding the problem really well and finding which model you can use to solve that problem really easily. A quirk about this model that you wouldn't know if you didn't do some research beforehand is that you need to write out a task prefix, for example. This is how the model was trained, was with task prefixes. This particular model, this version 1.1, they took out all of the pre-trained tasks, but it still works with the prefixes the same as the regular T5 did. This helps the model perform almost a categorization on the initial input text to figure out what's a good thing to do with it before it even processes the input, or like during that processing step. So because we're wanting to predict which emotion out of the 6 are in our data set, we're just going to do predict emotion, but you could put anything there. So let's keep going with our tokenize function. So we need to prepend that task prefix to every single row in our data set. And we're going to call that T5 prepared text. Task prefix plus text. So this should be able to work on any of our 3 portions of our data set, because all of them use text and all of them use label. So that's one of the things that I'm looking at as we write this, to make sure that it actually works for all of them. So tokenized text, as per usual, we're gonna grab our tokenizer and we're gonna do T5 prepared text. And similarly to the GPT models, we want to do max length for our padding to make sure that the decoder side works really well. Truncation equals true, and max length equals 256. If you're running into memory issues, shorten this and make your batch size smaller. I can't repeat it enough because so many people ask. Labels, if I could type it. Tokenizer, string text, label. We're converting it to a string because all of these are currently integers. You'll notice there's no quotes around it. That's just why we're doing that. We're going to do max length padding for our labels as well. Truncation is true, and our max length, because each of these is going to be an integer between 0 and 5, I'm going to do 4 just because, and I'll explain the reason for this. Sometimes these can get longer because you're going to grab end of sentence tokens, you're going to grab beginning of sentence tokens during this tokenization process. And so that gives us a chance to have a beginning of sentence token, a padding token, our actual label token, and the end of sentence token all at once. And if it goes longer than that, we have room to truncate. That's why I'm not doing 1. If you try this, if you put a 1 here and then have truncation equals true, you're going to throw in an error every time because it's going to truncate by 1. It will have nothing to take away. And then we need to add those labels into our tokenized text before we return it. Something that you can do to take full advantage of the encoder decoder structure is also create from these labels some decoder input IDs and decoder attention mask and name them as such in your tokenized text. You have to be careful when you do it, not for error, not because something won't work, but because there's a high chance of getting errors. You need to make sure that your matrix multiplication is really good for it. Because however long those are, your model might interpret that as an extra dimension on your input IDs. So make sure that you tell your model what is going into it by way of your training arguments. Don't just send it through vanilla style, because it will run into a dimensionality problem, because it will multiply the length of your input IDs by whatever the length of your decoder input IDs is. And same for the attention mask. Okay, and then we're going to map this. Well, first we're going to check whether or not this works. We don't need to. Alright, perfect. So we have our input IDs. You'll notice we have our 1 is our end of sentence token. Our 3 is our... I'm not sure if that's a beginning of sentence token or if it's a token representing this colon. Either way, this is pretty much the split. Oh no, this is end of sentence, this is beginning of sentence, this is the colon. So that's where it splits. So this is our predict emotion, probably predict emotion in those 4 tokens. And then this represents our I didn't feel humiliated. And it may not have broken that down exactly, but this is like the GPT-2 and the BERT tokenizer. This T5 tokenizer is a byte piece, byte pair encoding tokenizer. If you want to improve upon that, you have word piece, which looks at all the subword byte level encoding stuff and tries to create words out of it, which it tries to do it in a more human readable way. And Unigram, which word piece is a predecessor of Unigram, tries to do the same thing but ignores human readability and does it heuristically, as opposed to by frequency, which is what the byte pair encoding does. I'll do a video later on about pretty much everything you could possibly want to know about tokenizers, and we can get into that. So let's map this now. And then print yes. Oh, sweet. So you can see I've already done this. And if you don't put load from cache file equals false, then it will just grab whatever was in the cache. This is a really cool innovation by Hugging Face, and I mean, I'm here for it. This is what it looks like when you don't do that, though. It'll take about, what, 6 seconds to tokenize everything. Really, really quick. Why are we erroring? Oh, cannot create a file when that file already exists. Okay, so here is something pretty cool about this. So, if you go into your disk drive and you go into, on Windows it's users and then your username, and into this folder cache, there's a Hugging Face folder. And I don't know if there's a good way to show you this without compromising some security. Maybe this should be fine. So within this, you can grab your data sets, you can grab your text. Emotion is the data set that we're looking at here. We could probably delete all of these just rerun stuff. It's having to re-download the data set because we deleted the cache. It's having to re-download. Oh, it won't have to re-download the model because we didn't delete that. Oh, now it has no problem. Perfect. Perfect, perfect. So now we have an encoded data set with all of the exact same features as the past one. So let's go on to the new thing that I wanted to show you guys, which is how to create your own metrics computing function. I'm going to just call it compute metrics. And what this is going to take is a prediction from the model, or I guess many predictions from the model during an evaluation step. You're going to grab your labels from those predictions. Pred.label IDs, that's how that's stored. And you can find this in T5 output on Hugging Face to be able to know what to call in here, which methods. You want to grab the actual predictions, which is pred.predictions. And this is a tuple object, so you can either do the first one. First one's probably best because you're returning one prediction. If this were an actual sequence to sequence thing, like a translation, you'll want to return the entire predictions list, or do an .argmax -1, just like that. For our purposes, we don't need to do that, but you may run into errors, and that's what's going to be the error. So this is the F1 score that we imported from sklearn. Labels, preds, and we'll do a weighted average. And then accuracy is the accuracy score, and we want to do the exact same thing. Labels, preds, but no average. And then we can return. And we need to return a dictionary every time. So if you want to add to this, if you want to calculate rouge score, for example, or blue score, for example, you can do both of those, no problem at all. Just make sure to return them in the dictionary. This can be as big or as small as you need it to be. And now, our data collator, let's instantiate that. Tokenizer. Let's scroll down so I can actually see the suggestions again. We want to pad using the same way as our tokenizer did. and we want to pad to the exact same max length, which is 256. You can change this number. Again, please remember to change both here and here if you're running into memory issues. So that's instantiated, and now training args. And for this, we're going to do output directory equals T5. Evaluation strategy, because we actually have a validation data set, we can evaluate by epoch or by epoch, which means that we need to do more than one training epoch, otherwise it's not going to evaluate, or it will just evaluate once at the very end. Yeah, that should be fine. Report to none as per usual. Learning rate. This is another quirk of the model. We want to do a learning rate that's a little bit higher than normal because it has the capacity to learn a lot faster without running into significant issues. Thanks in part to the Atom W optimizer that is the default for this guy. But yeah, in any case, this was tested at a learning rate that was lower than this, lower than 1 e to the -4th, and this is one of a couple of suggestions of where you might start with your learning rate, just a bit higher, to try and get it to converge quicker. Save steps, you can put whatever here. I'm just going to put 500. There will, because it's 16,000 rows, depending on your batch size, there will be about 20-ish thousand steps, or I guess 12-ish thousand steps is what I'm trying to say actually. Say total limit. You want to do this so that you don't run into you don't accidentally overfill your hard drive. And then we want the training one first. Per device train batch size. You can do 4, 8. I'm going to do 16. I know that mine can handle this. If you run into memory issues, definitely decrease that. The eval batch size, you want to be a lot lower than your training batch size. If you run into memory issues when the eval batch size starts, you should decrease your training batch size, because it's going to keep whatever it trained on loaded into memory and try to load the entire evaluation batch, which is 2,000 rows at once. If you run into significant issues, get rid of this evaluation strategy and get rid of this per device eval batch size. And you may want to even add in, what is it, do eval, let's see, false in here to make sure that it doesn't actually do this if you're running into too many memory issues, because you can evaluate after. It's helpful to the model to evaluate during, because it can use it to help back propagate a little bit more efficiently, but it doesn't have to. And we have a test data set as well that we can test after the model is done training. And trainer equals trainer, model equals model, args equals training args, data collator equals data collator. Training data set is our encoded data set, but only the train split. And eval data set is our encoded data set, but the validation split. And our compute metrics is our compute metrics function. This will take a function. And then we are ready to go. Oh, we need commas. Trainer.train, trainer encoder.save model. And I'm not going to run this because I've already done it. Instead, I'm going to click and drag the model into our folder. And the model ends up being a little bit under 1 gigabyte. It's a lot bigger if you're loading from a checkpoint because there's a lot more to do. But it's pretty big. It's pretty nice. So here's where we're going to actually load it up and use it. G5 for conditional generation from pre-trained, and we're just going to pass in the folder where we're keeping it. We'll give it some text. Stop doing that, you jerk. Inputs equal tokenizer text. And because we're actually running this, we want to return a tensor. I'm just going to do PT. You could do TF if you're partial to TensorFlow. And so this is where you run into some really cool stuff with encoders or decoders. Encoder and decoder models. Encoder decoder models are able to both have a forward method and also a generate method, and so you get to pick what you're going to do with them. Generally, your forward method you're going to use if you're still wanting to add training to the model, maybe one portion at a time, or you're trying to evaluate, or you're trying to predict on that test set. If you're just trying to see what does the model do, use model.generate, and you have to give it the keyword inputs because your tokenizer returns a dictionary, and then print. Actually, I'll show you this. Print out so that you'll see why. It's going to give a numerical list, a big ol' array at the end. That's why these are sequence to sequence models for conditional generation. So we then have to decode that again. Decode out, and we're going to decode the first. So this is the output from loading up our model. This is what it looks like. This is what you would pay attention to for your config file. This is what it actually outputs, a tensor. And then this is what that decoded tensor looks like. So you'll notice it's labeled 0, which is the same as these guys. I'm feeling rather rotten, so I'm not very ambitious right now. I'm feeling quite sad and sorry for myself. I didn't feel humiliated, which I guess those are a little bit more dejected than angry, but that's pretty good. And you can test this. When I tested it, it got about 89% accuracy. This is a usable model. And that is where we're going to leave it for encoder and decoder models. And I will come back next time with more. We're going to be doing probably tokenizers and feature extraction and maybe even something cooler. So I will see you guys later.